when we said that there is a projectile or a particle which is basically coming and hitting the target, this projectile is either going to affect the reaction, okay, and then we basically call it a compound nuclear reaction because it will have an impact, okay. It may actually change the property of the nuclei. The incident particle may itself change, okay. Apart from that, we may also call it as a direct reaction, where the time period of interaction of this target, okay, with the of this nuclei with the target, okay, or this incident particle with the target will be very less in time, of which there might not be a very strong reaction that might be happening. There might only be something which we call as scattering. Okay. We also saw that how exactly we represent an equation, nuclear equation, that we already know. And apart from that, if we just consider the normal reaction, what we do is this. Okay. So what we do is this, that when you have this as the projectile and this is your target, okay, you will get a nuclei which may be unstable, okay, and then this will actually give rise to a totally different nuclei, okay. The target property will change apart from a outcoming particle. So you might have a proton changing to deuteron and so on, okay, and they actually can be differentiated in terms of the de Broglie wavelength. So this is something which we saw, that in case this de Broglie wavelength, which we know that all uh, particles will actually have associated with it, if it is comparable to the size of the nuclei, we actually can consider, or we can, if it's comparable to the size of the target nuclei, we can say that there will be a compound reaction. Probability of compound reaction will be far greater. Okay, and we can actually calculate the de Broglie wavelength of proton or electron or neutron, and then see if it is comparable to one forming or two forming, and then we can actually predict whether there is a chance of compound reaction or not. So we do also to understand that the time period is a very important role, that how long does it have to actually interact. Okay. So what happens is that if this de Broglie wavelength is small, okay, small is the keyword here, comparable to the, let's say, one nucleon, okay, then there are chances that there will be only a direct reaction. Okay. So if you have a very heavy object, a heavy object, chances are that the deformation will happen for both the objects in general. Right? But if we have a very light object hitting a very heavy object, the chances are that there will be no deformation at all. Okay, at least for the heavy object, there will be no deformation. Okay? That is the general idea. But if you are considering, let's say, the example that I've given, if you have got a very heavy, let's say, pinball, okay, and you are hitting it with a plastic ball, and then there will be deflection, the chances are there will not be any kind of reaction. So we have to understand this, the time of interaction, and of course the mass plays a very important role. Okay, and based on this, we actually can have a very clear idea. So what we can do is, based on this, whatever I said, we can actually differentiate between a compound reaction and a direct nuclear reaction. This was a question which I've given in the mid-sem of last semester, I guess. So it was a 2 marks question, and whatever I've said, you can explain. Okay. So today we are going to continue with this, but this time what we are going to do is we are going to look into an example. Okay. So whatever we are going to learn in this unit is not going to be very difficult. Okay. You have to just understand that some basics needs to be clear. Okay. And then step by step derivation of equations and all will be more important. So let's say I have got a proton. Okay, and it is hitting a copper, which is 63. You know, there are different isotopes, but let's just consider the 63 copper. And then if it's the proton, it will basically be equivalent to 64 zinc, which is more or less unstable. Okay, so in nuclear reaction, whenever you are using an asterisk sign or a star sign, you're basically saying that this is unstable. That means the chances are there that it is in an excited state. Okay. Another reaction that we can consider is an alpha particle. So see, if I ask you what is the difference between compound reaction and direct reaction, in compound reaction also you can use an example to explain. Okay, you can just take this example. So you have got an alpha particle hitting a nickel. Okay, and you know alpha particle, the value of K is 4 here, right? So if this is 4, you can just take it to be 64 nickel. Again, then there are chances that it will actually give out a different nuclei altogether. So if we just consider that, we will just take this zinc problem. So let's say this 64 zinc, the chances are you will be getting 63 zinc and neutron. 64 zinc, the chances are 62 zinc and 2 neutron. And 64 zinc, there can also be 62 copper plus proton plus neutron. So all three possibilities are there. So now you might ask me that which one is more correct. But see, the thing is, whenever there is a nuclear reaction, there is a lot of probability involved. For example, if you basically consider the reaction that happens in sun, it's not that you are only getting hydrogen combination and you are just getting helium. Right? Helium will again combine. It will give you lithium. It will also give you beryllium and all. Okay, so the chances are that maximum helium will be formed. So it is more or less probabilistic. So since more helium is formed, and we actually can also do an indirect measurement of that, that there is more reaction where helium is formed. Based on this, we can say that the chances are there is more helium. So this is what is actually done. Okay, so there are possibilities. So by possibility, I mean that there might be different probabilities of happening, but in case the probability is 4 for 1, okay, then the chances are that this reaction will occur. Okay? So you have to please keep this in mind that nuclear physics is also dealing with quantum mechanics, and probability plays a very important role. Okay? If I take today's example, let's say you are doing a COVID test. Now, if you do a COVID test, you basically have got a RAT test, right? Rapid antigen test, and you have got an RT-PCR test. Now, if you take a rapid antigen test, and if you're getting negative, still there is an advice that you be in quarantine. Okay, so what is the reason? Because the rapid antigen test is not 100% perfect, but this is probabilistic in nature. But then, if it's probabilistic in nature, how much probability is there that you are actually affected by COVID? The chances are only 20%. If rapid antigen test is conducted and your it's negative, you mean that 80% chances are there that you are negative. That means you are not infected by COVID, right? So, but still you have to go to quarantine because there is a 20% chance that you might be affected. Okay, and that's safety reason. So, probability plays a very important role in our day-to-day life. I think this is the best example we can take. So please don't, and whenever you see any kind of nuclear reaction, and there are 2, 3 reactions given at a time, like for example, the sun's reaction, which you might have already seen before, there is a proton cycle 1, proton cycle 2, and proton cycle 3. All the probabilities of each of these reactions will be different. Okay, so whenever you see into this, don't get confused. Okay, it depends on what are the chances of a reaction happening. Okay, that is very important. Okay. So let's talk about direct reactions now, okay? And when we talk about direct reactions, there is also something which we call as the transfer reaction, okay? So here we are talking about a direct reaction. I think I should not mention direct reaction here. I can take a direct reaction later, okay? I will just talk about compound reaction now. So let me just cancel this part. I'm not talking about. I'm just talking about the change, okay? So what is the change that I'm talking about is this. So let me take the first example here. So the first example says that you have got a target and you have, let's say, a projectile D. So that means a deuteron is hitting a target X. So this is X, okay? And a deuteron is hitting that target. And when the deuteron actually interacts with the target, the particle that comes out is nothing but proton. So what does it mean? That deuteron is nothing but 2H1, right? We already know it is 2H1. So that means if the target is proton, that means one of the neutron has been absorbed. Okay, one of the neutron has been absorbed by X, and this X has become Y. So what is happening? That one neutron is actually stripped off. One neutron is actually stripped off the deuteron, and that is why this is called a stripping reaction. Very important. Okay, and this is actually very simple also to understand. You might also have that target is there, and then you have got a projectile deuteron hitting it, and then the chances are that you might actually get a neutron out of it, and the proton is being absorbed. Okay, so that means the proton is stripped of deuteron, and then finally we have got Y. So that means the A value of Y will increase by 1. So if this is A, okay, this will be actually nothing but A plus 1. Right? This will be A plus 1. So what happens is it is actually getting a neutron or a proton. So that means there is a stripping of happening, and that is why it is called a stripping reaction. So it should not be very complicated, very simple. And I think the other two terms are also quite simple to use now. So now what we have is target, and now what happens? We have a projectile which is not neutron but proton. So if a proton is hitting a target, and the outgoing particle becomes deuteron. That means the proton has actually in the process captured, okay, or picked up we should not say capture here, it should not be picked up, okay. It has picked up a neutron from the target. It has picked up a neutron from the target and has become deuteron. Since it has picked up a neutron, the A value has changed, so that means the target nuclei has also changed. So this is called a pickup reaction. So what can I ask you in exam? I can give you a reaction and ask you whether it is a stripping reaction, pickup reaction, or capture reaction. So if you understand these three lines, okay, on this single slide, I think this is very simple. Okay. Third, we have a target and we have got a neutron. Okay. And then what happens is it is absorbing the neutron and giving out only gamma ray. Okay. So giving out only gamma ray. So when it gives out gamma ray, that means you don't have a particle which is coming out. You have got just energetic photons which are coming out of the system, right? And that is nothing but the neutron has been captured. So that is why it is called a capture reaction. So there are three types of reactions that are possible. Whenever there is a change of the target, it changes from X to Y. It might be a stripping reaction, it might be a pickup reaction, or it might be a capture reaction. Okay? So these three points are very important because you usually look into a reaction and answer those questions. Okay, I have seen in some net and gate exam also they do ask this question. Okay, but this is not a very popular topic, but still the chances are there. But this is a very simple idea. You understand, remember it forever. Very complicated. So there is one more difference between compound reaction and direct reaction. Okay, and whatever we have discussed before, I'm just adding that. Okay, I'm just adding that. So the one of the important reaction is nothing but the time scale, for how much time the reaction is happening. Okay, that actually depends on a lot of factors. What is the de Broglie wavelength? That is also an important factor. Okay, so whenever we are considering a compound reaction, we do understand easily that the time for reaction will be more. Okay, and that reaction time is 10 to the power minus 15 seconds. Now, in our real day-to-day life, 10 to the power minus 15 seconds might not matter much. Okay? Like 1 second even doesn't matter. Okay? Sometimes the day before exam we study. Even the entire year doesn't matter sometimes. But then for nuclear reaction, if the reaction happens for even a very short period of time, the chances are there that something drastic might happen, something drastic might change. Okay. For example, let's take the atomic bomb or the nuclear bomb. The reaction doesn't take that much of time, but that in that scale, in that atomic scale or in that nuclear scale, this value of 10 to the power minus 15 seconds is large. Okay. So this time is actually enough for the energy to be transferred and distributed. So I hope you understand this because you have a compound reaction. It means that the energy from the target, from the, let's say, the projectile or the particle hitting the target, it needs that much time to transfer its energy. So this much time is enough. And this time that we are talking about for a direct reaction is actually of the order of 10 to the power minus 26. Okay, if we're talking about direct reaction. So compound reaction, 10 to the power minus 15 second. Direct reaction, 10 to the power minus 26 second. So you have seen one more point of differentiation. Okay, and whenever you write down an answer, probably using more values would be good. Okay, now I have taken an example to estimate why it is 10 to the power minus 22 second. Okay, we really don't need to go into a nuclear lab and do the experiment. We can actually do it simply here. Okay, just simple calculation should actually suffice. So what happens is this. Let's consider a proton, okay? And this proton has got an energy of, let's say, 20 million electron volts. Okay, and that's a standard energy of a proton. Okay, and how do you get that much of energy or vary the energy? You can actually use something which we call as the particle accelerator. So those experimental setups that we have in CERT, okay, Geneva transporter or Switzerland transporter, or we can talk about something like cyclotron, which you have studied in your lower classes. Everything is actually there, and those are helping to actually generate proton of, let's say, this much energy. So what is this energy? This energy is nothing but the kinetic energy. So we can simply write down this as half mPv square is equal to 20 mPv. And from this, I can find out the velocity. Very simple, right? I can just take v is equal to root over, uh, let's say, I'll just simply write it down as root over 20 mev, okay? And then there is a 2 here, so this 2 gets multiplied, so this will become 40, right? 40 mev divided by m, okay? And then what I can do is, in order to change it into relativistic, the conversion of 931.5 mev, I'll just multiply it with t square. Since I multiplied it with t square, I should also multiply here with t square, and that will come out of the root, it will be just c, okay? So more or less the equation remains the same. And let's assume, okay, because see, we are considering the order here. So even if I don't consider it to be 931.5 MeV, let me just consider it in round figure, 1000 MeV, okay, approx. So if you just do that measurement, what you get is 0.2 into 3 into 10 to the power 8 meter per second. Okay, think about it. Why It's already know we are converting that mass into energy, and then we can actually find out what is the velocity. Okay? So we are doing that equation. Dimensionally also this is correct. If you check the expression and convert MeV to joule and everything, it will get in meter per second. Okay? But you don't need to worry because we are doing it so many times. It should not be very difficult. Okay. Now let's do this calculation of time. Now it's very simple. Okay. So what we are doing is we are going back to the basics. Velocity is equal to distance divided by time. So time is equal to distance divided by velocity. But what is the distance? Okay. The distance is, let's say, the nuclear size, because in case it wants to have a reaction, okay, we can assume it to be within the range of the nuclear dimension. Okay. So even it might be a bit far from this. Okay. But let's say this is around 10 for me. Okay. So what is the nuclear dimension? Around, let's say, 1 to 2 for me. And the impact, let's say if it's a proton and the target is a positive nuclei, there will be a deflection. And the impact can be felt, let's say, up to 10 for me. Okay, just assume it. Don't worry. The order is important. 10 to the power minus 15 is more important compared to the 10 or the 5 that we have before. So time is equal to distance by velocity. So the distance that it has to cover is nothing but the size of the nuclei. That's 10 for me. Unit is distance divided by velocity. So what is the velocity that we got is this. So we can just take this divided by this. If you do this calculation and do all your sums here correctly, you basically get the value to be 10 to the power minus 22 seconds. So what does it mean? It means that if you basically have a proton, okay, and if it's not a capture reaction, okay, uh, and the time that it basically has is 10 to the power minus 22 seconds, okay, with this energy range, and that means that the chances are that this will be a direct reaction and not a compound reaction. Okay, so the chances are there will be a deflection. So when we studied about scattering in our second unit, this is the time range actually that we have considered. Okay, so that is why this actually becomes a bit important also. So this is something, the idea is already there, but we are just doing it in terms of the development of the time scale. Okay. So see, if you ask me where do I get this calculation, you won't get it in books. Okay, I have not seen any direct calculation for this on the book. I have got this from a video lecture that I've watched. Okay, so if I've seen that and they have done this calculation, I thought that okay, this is relevant, so I just put it here. Okay, so I have just compiled the lecture in such a way so that we are also able to get some values. Okay, that, so we have this. So in exam, I might ask you that show that a proton of energy, let's say 20 MeV, okay, will actually initiate a direct reaction and not a compound reaction. And just simply write down this, do the calculation, show this. So question can be tricky, okay. As I said, every time, every now and then, asking question is more easy, answering is a bit difficult. But to understand the concept, answering that also should not be very difficult. That's there. Now, let's talk about one more feature which is important in comparison for compound reaction and direct reaction. Mind you, the later points that I've included for compound reaction and direct reaction may be an answer to a descriptive question. Differentiate between compound and direct reaction. Objective question you might be 2 marks, but descriptive it might even go up to 5 marks. So you have to explain these factors. Okay? So angular distribution of the outgoing particle. So the angular distribution of the outgoing particle should not be very difficult. Okay, it's actually very simple. So we're talking about the angular distribution of the outgoing particle here, and then we are not going to talk about the energy here right now. We are just going to think something which is more basic in nature. So what happens in compound reaction is that the outgoing particle might have been distributed in different directions. Okay, so understand it in this way. If we are considering something like a direct reaction, the chances are that there will always be a forward peak. Now what do I mean by a forward peak? So I've already drawn it, but let me just draw it again. Suppose we have this target, okay, and then we have got a very simple particle, and then it comes here, and then this is a direct reaction. So this is going to happen this way. You have got one more particle. If you have a beam of particle, it will happen that the next particle might direct in this way, and then this way, and this way, and so on. So see, what is happening is it is basically forming a forward peak. It is forming a peak which is in the forward direction, and that is why we call it as the forward peak. Okay, so a forward peak is expected. Mind you, it is expected. So the probability is forward peak. The probability is forward peak. Okay, So what about compound reaction? Here what happens? The distribution is likely to be symmetric. So symmetric means that the chances are that the outgoing particle might also be deflected in a reverse direction altogether. Okay? So that is important. So that is another point of difference here. And if we say that, that means that the angular momentum distribution will be different for both the cases. So we are not analyzing this directly. What happens is if we are considering in particular an angular direction, what we do is we are going to see a different distribution of angular momentum altogether. Okay. So this is what I wanted to tell you for this class, and in the next class we are going to look into something which is called an energy conservation. But then before the next class, let me just give you this whatever I said at the beginning. Okay, so if you are considering any kind of nuclear reaction, the energy conservation is a very important concept. So how do we start with energy conservation idea? What we say is we are assuming that it's a compound reaction, not a direct reaction. So what we say is in a compound reaction, we do have the uh, particle which is actually initially at rest. Okay? It is initially at rest and then it starts moving and it hits the target. So if we go into calculation part, this is moving, but then this is at rest. But that is before collision, okay? Before collision. And after the collision, both the target as well as the particle A will actually start moving. So you have the particle A hitting the target, and then you have got a detector, you have placed a detector somewhere which detects the particle B, that is the outgoing particle. Okay. But then this A has an impact on X. As a result, this has changed to Y. Okay. But then both of them are deflected at a different angle. Let's say B is deflected at an angle theta, and X is deflected, which has become Y at an angle phi. Okay, so the target is at rest is a very important term here. And then if we actually want to look into the energy conservation, what we say is this. First, write down the reaction. Once we write down the reaction, we can simply say that this is A plus X will become Y plus B, right? So I think we have already seen this. So whenever I write down in a nuclear reaction, even if you write it down in this way, X, A, B, Y, fine. Okay, so this is the same representation. This is how you represent a nuclear reaction. Okay, don't interchange B and A. It should be A, it should be B. Don't interchange X and Y also. Okay, important. So as I said that this will actually have an X component. Okay, and then a Y component. This will also have a X component. Okay, and then a Y component. So if you look into the theta part, the X component is along the X-axis. Okay, and this would be nothing but, let's say, if we resolve the momentum. Okay, will be along this direction, but then the phi part, the X-axis will also be in this direction. So that means both of them are adding to the X component of the momentum. But then if you look into the Y component, both of them are in opposite direction, so they will be subtracted, right? So this is what we are going to do in the next class. We are going to look into this energy conservation, and we are going to find a relation based on which I can predict what is the kinetic energy of B. Because this is an incoming particle, I can actually control its energy, right? As I said, proton is 20 MeV. How do I know? Because I have controlled it, right? I have applied a magnetic field and an electric field, controlled it, and provided a kinetic energy. If I'm able to control it, I know the value. But then for B, I don't know what is going to happen to the outgoing particle. If I know what is the kinetic energy of the outgoing particle, then I use the conservation of energy and momentum. I can predict what is happening to the target.